This lesson is for day 7. We're going to be looking at graphing exponential functions. So our objective for the day is to graph an exponential function specifically using a table. There are other methods, but we're going to work on just using a table right now. And we're going to also identify the x and y intercepts as well as the domain and range for this function. Now, the second objective written here is actually for a later lesson. So today we're only working on objective 1. Now, I want to talk about what an exponential function is because this is a new graph that we are now studying. Okay, now here are a list of all of the types of graphs that we're going to study for this semester here. We've looked at linear functions already. Linear functions are in the form y equals mx plus b. We've looked at absolute value functions when we get that v shape. We've looked at quadratics when we get that u shape for the parabola. Here's the vertex form for a quadratic as well as the standard form of a quadratic. What we're going to be specifically looking at in this chapter is exponential functions. Now an exponential function is in this form here, y equals a times b to the x. Notice where your variable is, your x, your input is actually an exponent, which is why it's called exponential. Okay, so it's different than any of these where we don't have the input here, our x inputs are not exponents. So here's the general form for an exponential graph, and we're going to start looking at graphing some using a table. Okay, let's look at our first example here. It says to create a table of values and to plot the points on this grid. So here I've got to sketch the graph of f of x is equal to 3 of x. Now remember, f of x is the same as y, so we're really looking at y equals 3 to the x. Now I'm going to just start with our standard -2 to 2 table and see what values we get. So if I plug in -2 for the x, remember it's in an exponent now, so I end up with 3 to the -2nd power, which is the same as 1 over 3 squared, which gives me 1/9. So I'm plotting the point -2, 1/9. When I plug in -1, I should get 1 over 3 to the 1st, so I get 1/3, and then -1, 1/3. So really we're going to be practicing a lot of exponents here, so that's kind of nice. You're going to get a little bit of review there. 3 to the 0 power is simply 1, 3 to the 1st is 3, and 3 squared gives me 9. So here are the points that I want to plot. Okay, so I would like you to pause the video and plot these points here. You don't have a scale necessarily. You guys can create your own scale if you would like. You can put your axes also wherever you want, wherever it's convenient for you, looking at your points here. We want to make sure we can go up to at least 9, right, in the y values. So go ahead and plot those points. So here are the points that I plotted. Now, even if you guys did not use the same scale as I did, and even if your x and y axis are in a different spot than mine, you should get the general shape that looks very similar to what mine looks like. So I want to talk about the general shape of an exponential function. Remember, it looked kind of like this. So the points kind of look like they're already following that, and I didn't even graph that many, right? I only graphed 5, and I just graphed the standard -2 to 2. But I'm going to draw in a curve here. It looks like this. I'm trying to show, this is probably not so great of a job, but I'm trying to show that this is really, really close to that axis, but not actually touching it. So I'm graphing a smooth curve, kind of like that. Okay, and I am showing that it's going to continue in the negative direction, all the way to -infinity, but I'm trying to show that it's not crossing this x-axis. Okay, so let's talk about why I'm drawing it that way, but I want to first take a look at x intercepts. So we have to still find x and y intercepts, our standard information. We're also going to talk about the domain and range of an exponential graph too, as well as this new word here, an asymptote. And you can look at the definition here, and I'll go over that in just a second. So let's talk about an x intercept. When we find an x intercept, this is saying let y equal 0. Now if y equals 0, then in our function y equals 3 to the x, I plug in 0, and I solve this equation. Now this equation has no solution. Okay, and that's because you can't plug in any value for x here and end up with 0 for the output. Because think about it, we already plugged in some negative values, we plugged in some positive values, we even plugged in 0 here. 3 to the 0 gave us 1. If we started to, let's say, try to plug in very small negative numbers, so let's say a really, really large negative would be something like, I don't know, -1000. Well, all that negative does is it changes the base and makes it in the denominator, but it doesn't make it a negative value. It just makes it a very large number in the denominator. So you're dividing 1 by a huge number here. Because if you think about it, 3 to the third is already kind of big. So 1 over 3 to the third is 1/27. 3 to the fourth then would be 1 over 81. And then 3 to the fifth, 243. I mean, it just keeps getting bigger and bigger and bigger. This number here is a bigger number than 1 over 81, right? This is smaller. 1 over 81 is smaller. And 1 over 243 is even smaller. They keep getting smaller and smaller as you increase this number and make that more negative, okay? So I'm showing that it's going to continue here in my graph, right? It's going to negative infinity, but it's never going to cross this x-axis because it doesn't ever equal 0, and it's also never negative. Notice all of these values here are positive. Even 1 over 3 to the 1,000th power is still a positive value, okay? So in place of writing a coordinate here for our x-intercept, what you're going to write, since there is no solution, there's no actual x value that will make that equal 0, you're going to write does not exist, DNE. So an exponential function is not going to have an x-intercept in this case, okay? So this particular exponential function does not have one. Now a y-intercept just means that you're going to say x is 0. So you're looking at y equals 3 to the x and plugging in 0 here, and we actually already found this. Y is going to equal 1, right? We have that coordinate right here, so that's consistent. It matches with what we graphed as well. This function is crossing at 0, 1. And so when we talk about the domain, we could plug in anything in this table, right? There is no restriction on what we can plug into this table because we're going to get a real value no matter what we do. So this is all reals for our domain. However, our range, though, is only values that are positive. So y is greater than 0. I'm not writing y is greater than or equal to 0 because it cannot equal 0. It's only positive outputs. Okay, the y's can only be... Okay, the last thing that we're going to talk about is an asymptote. Now, here's the definition right underneath, but an asymptote is just a line in which a graph gets arbitrarily close to it, but it never actually touches the graph, as your independent or dependent variable gets very large. So we're specifically looking at here where we talked about when the x gets very, very negative, right? A very large negative value. So as it continues to negative infinity, this value doesn't ever get to equal 0. It gets really, really close to 0 because if I continue to divide values like 1 over 2 to the 1 over 243, and then 1 over 3 to the 6th, and 1 over 3 to the 7th, and 1 over 3 to the 8th, they keep getting smaller and smaller and smaller. These decimals get smaller, but they never actually become 0, okay? So what I have then is, it's called an asymptote. It's a horizontal line in this case. You can have vertical asymptotes, and we're going to study that in second semester. But these particular functions, exponential functions, have horizontal asymptotes, okay? And in this case, I'm going to show that by showing a dashed line at the line y equals 0. So I have an asymptote that exists at the horizontal line y equals 0. So that's what I'm also going to write over here, y equals 0. Remember, this is an equation of a line, so make sure that you're writing y equals 0, not just the number 0, okay? Oh, I want to clean up this y-intercept. Just make sure you're showing it as a coordinate also. Here I had the x-intercept does not exist because it doesn't ever cross the x-axis. My domain is any real number because I can plug in anything I want into the left side of this table, but the only outputs that I ever have on the right-hand side are only positive outputs. Okay? Let's try another problem. All right, we're going to sketch the graph of 2 to the x plus 4. Now, when we think about translations and transformations, this plus 4 is similar to seeing something like y equals x squared, our mother function, plus 4. Remember, that only moved up that function 4 units. So this is actually what's going to happen too in this exponential graph that we're going to show in just a second. But I want to first just graph our table because that's what our objective is to graph using a table. So if I pick our standard values, -2, all the way to +2, I have 2 to the -2nd plus 4, right? If I use order of operations here, 2 to the -2nd, then plus 4. So this ends up being 1/4 plus 4, which if you want, you can change this, into 16/4. Find that common denominator and add. But I actually don't want to do that here, and I'm going to stress that you probably shouldn't either, because it's harder to graph 17/4, I think, for you guys anyhow. It's easier, I think, if you just keep it as 4.25, right? 4 1/4 is 4.25. Or you can, even leave it as 4 1/4. Because it's much easier to graph this, I think, than 17/4. Anyhow, if we plug in 2 to the negative first, we get 1/2 plus 4, so 4 1/2 is 4.5. If I plug in 0, I get 1 plus 4, so 5. And plugging in 1, I get 6. Plugging in 2, I get 8. So let's take a look at what these values now look like. I have -2, 4.25. Let's do this in another color. I have -1, 4.5. I have 0, 5. 1, 6, and 2, 8. So this actually might seem really, really easy, finding these points here and just plugging and chugging. But for some reason, you guys tend to make a lot of small errors in this. So please be very careful when you're filling out this table, because if you get a table that's inaccurate, when you go to plot your points, you're going to have no clue why it looks all funky. So please make sure that you're being really careful with this mental math here, because you're not going to be able to use a calculator. So continue to try your homework without a calculator, because you will be assessed without a calculator. So make sure that you're setting yourself up for success, okay? Don't use a calculator in your homework. Now, I'm going to plug in just one more value here. If I do 2 to the third plus 4, now I have 8 plus 4, so 12. And that's because I want to see or show you that these are not increasing by the same value, right? This y output here is not increasing by the same exact value. It starts to get pretty big. If I plugged in 2 to the fourth, I'd get even larger values. So here's our last point, 3, 12. All right, so I want to go ahead and have you plot these points so that you can practice that, and then we'll talk about the function in just a second. Okay, so I kind of cheated a little bit. I'm using the key that I already made in order to show you what this graph looks like. But basically here, your plotted points here for the -2 to 2, that standard table. And I want to show you how the new asymptote has actually just increased, right, to y equals 4. It's moved up from y equals 0 to now being at y equals 4. And that's because we're accounting for the fact that everything has been shifted vertically up 4 units. So remember how our old point was at 0, 1? Well, now that new y-intercept is actually at 0, 5. And you can see that too when we plotted the point, or I'm sorry, when we plugged in to our function here, 2 to the 0 ended up giving me 5, okay, when we plugged in x to 0. So everything's been shifted up, and it's really just tying into the whole idea of transformations that we've been studying for quite a while, right? Transformations, this value is going to move it up. If you have a value here, it's going to move it to the left or to the right, the opposite direction. So I think it's kind of cool that it's tying in all those previous ideas for you now. Okay, now I already have a lot of this other stuff filled out, but again, just to reiterate, if you were trying to find an x-intercept, right, algebraically, here I have the work shown for it already, finding an x-intercept means that you're plugging in y is 0. So that's why I have y equals 0 here. And then I'm trying to solve the equation 2 to the x plus 4 equals 0. Well, if I try to isolate this 2 and try to solve here, I end up with no solution. There is no value for x that if I plugged in, even a negative value here, 2 to the -2nd power does not give me -4, it gives me 1/4. So there's no possible way that I can solve this equation, so this is why I'm writing here for the x-intercept does not exist. Now for my y-intercept, I think that's pretty straightforward. Plug in the 0, you're going to even see the output already. Our domain is still all reals because I can plug in anything I want here on the left side, but on my right hand side, this is where it gets tricky to see what your range is, okay? Okay, now when you're looking for the range of your function, it's probably actually helpful to continue to use more values in your table. So if you haven't already seen kind of what's going to happen with this, if you try to plug in, let's say, -3, 2 to the -3rd plus 4 gives me 1/8 plus 4, so 4.125. Now, even if I continue to put in larger negative values like negative, I don't know, 10 or something, when you start putting these values in, you'll still have a base of 4 plus some crazy small number, right? 2 to the negative 10th power is a really, really small number. But because you have that base of 4, you're never going to actually hit 4 because you're always adding some value to it. Even if it's really tiny, you're still adding something to it. So that's why here our range, it's never going to equal 4 because we're, again, adding some value to the 4, but it's going to come very, very close to touching 4, okay? Very close. So that's why our range here is y is greater than 4. So our asymptote is also y equals 4, and you can see here that I graphed that. I'm showing and labeling that asymptote also. You should always make sure that you're labeling that information as well. And yeah, that's pretty much what we needed to cover for the second graph. Okay, so I also have already written in here, since it's the key, but the summary of these two graphs. Now, in blanks here, it says, as x increases, y also increases. We call this an exponential growth function. And I want to talk about what that means by increasing and what happens with the y. So if you look at your x inputs here, you know, -2 is larger than -3. -1 is larger than both of those. 0 is larger. So these values continue to increase, right? So if I plugged in 3 here, what would happen over here? Well, these values also increase. 4.25 is less than 4.5, which is less than 5, which is less than 6, which is less than 8. So these values are continually increasing as I increase these inputs here, okay? So the reason why it's called a growth is because as you move in this direction, in your x direction, the y increases, okay? It grows. So this is why it's called exponential growth. Hopefully that makes perfect sense. Okay, now on the back side we have a different type of function here. F of x is the same as y, right? So this is y equals 1/4 to the x power. And I'm going to graph using my standard table, -2 to +2. So let's say I plug in -2 here, I get 1/4 to the -2nd power, which I could do one of two things. I can distribute that -2 to both and then move, or I can just take the reciprocal right away to that positive power here. So this is 4 squared, 16 over 1 squared, so 1. And if I plug in -1, using that same idea here, I can take the reciprocal first, raise it to the positive power now, so that's just 4. 1/4 to the 0 power is 1. 1/4 to the first is 1/4. 1/4 to the second power is going to be 1/16, squaring both the 1 and the 4. Okay, so I'm plotting these points here. And if you want to pause, you can also plot those points and even try to finish off some of this information here. That would be probably a very good use of your time. But we're going to go through this using the key also. Okay, so now I want to take a look at what's happening here in this graph. So I'm using the key because it's really hard to actually plot these points on my computer. But notice that the curve actually is going a little bit differently in terms of the direction, right? The last one, the growth curve, looked like this. Now we have this curve, which is looking almost like it's the opposite. Now, you're going to study this more so in pre-calc and look at transformations a lot. We're going to stress transformations. But I find that this is pretty interesting, and I think you might get a better understanding if you realize that 1/4, that base, can be rewritten as 4 to the -1st power, right? And then if you raise that to the x, that's really 4 to the -x power. Remember how in an absolute value graph, or even in a quadratic, let's look at a quadratic, we take y equals x squared, that mother function, that's an upward facing parabola, right? It opens up. If I take that and I make that the opposite of x squared, then it all of a sudden faces downward. Now, in this case, that -x makes it flip over the y-axis here, whereas this is flipping it over the x-axis, right? Your x-axis, the x is like a mirror. It all of a sudden flips over that axis. Here, we take an exponential growth curve, and all of a sudden it flips over this axis to look like that. So it flips over the y-axis. So kind of interesting, right? I think, for me, I'm a math nerd, maybe not to you, but I still find it interesting. So, you know, this is the general shape. Now, and when we find our information, we're going to kind of run into the same issues here when we find the X intercept. Algebraically, if you try to solve this equation, there is no solution. If I plug in y is 0, I end up with this equation, no solution, which means my X intercept doesn't exist. the y-intercept, plugging in x is 0, I get a value of 1, so my y-intercept is at 0, 1. My domain still remains all reals because I can plug in anything I want on the left side. However, my range, in this case, will always be greater than 0 because these outputs have to be positive. I can never get a 0 or even a negative value for my outputs here, which means, therefore, that the range is at y equals 0. These values, as I continue to actually increase here, if I made this 3 or 4 or 5 and I plug these values in, these values continue to get smaller. 1/4 is bigger than 1/16. Your next value is going to be even smaller than that. So, you know, it's cool to me, maybe not to you, but you're seeing basically the opposite trend, okay? Now, let's move on to the next graph so we can look at one final graph and then draw some conclusions here. So if you'd like to just fill out this table, you can do that while I show you why it works the way it works, but filling out the table I think is the hardest part because you can make the most errors here. So if we use our standard -2 to +2 here, I have 3 times this value 1/2 to the -2nd power. So really this is 3 times 2 to the -2nd power. If I put that up top, is going to end up as 4 minus 1. So 12 minus 1 is 11. 3 times 1/2 to the -1st power minus 1 is 3 times this number here is going to be just 2 minus 1, so 5. And then filling out the rest of this is a little bit easier, I think. So 1/2 to the 0 is 1, 3 times 1 is 3, minus 1 gives me 2. Then 3 times 1/2 to the 1st power minus 1 is going to be 3 times 1/2. Okay, so now we're dealing with fractions, so I guess maybe it's not as easy. This is 3 halves. 3 times 1/2 is 3 halves minus 1, which is going to give you 1/2. And finally, if I plug in 2, this is 3 times 1/2 squared minus 1. So 3 times 1/4 minus 1 is 3/4 minus 1, which is going to give me -1/4. Okay, so here I go cheating again. You can see my table here on my key is consistent with what we got, but I also plugged in 3 here for just another value because I want to show you that these values actually end up being negative. The reason why these are negative is because of this vertical shift. The entire function is being shifted down 1, so now we are getting underneath that x-axis. Okay, so it is possible in an exponential function for you to get a negative output, but that's only if it's been shifted down far enough past that x-axis. Okay. Now this value here though is never going to quite hit -1. If I continue to increase here in this direction, I get smaller and smaller and smaller and closer and closer and closer to -1, but it never actually can equal -1. So that's why my range here is written as y is greater than -1, and my asymptote is at y equals -1. Okay, so I still see this general shape here, which is different than our growth curve that we saw, you know, in the front 2 questions. But I want to look at the X Intercept here because something special here happens with the X Intercept. Remember, because it's shifted down, now all of a sudden I do have an X Intercept. Okay, so let's look at how to find that X Intercept. Okay, so all I'm doing when I find an X Intercept is to plug in y equals 0, right? So I'm really solving this equation here. Now, to isolate the x, I'm going to have to add 1 first. That would be my first step. And then I would divide by 3. So I have 1/3 equals 1/2 to the x power. Now so far what we've been working on, when we try to solve an equation that looks like this is just an exponential equation, we try to write this having the same base. Now unfortunately in this problem there is no way for us to write this using the same base. Now this is a little bit advanced for us right now at this point because we haven't studied a new chapter yet, which is called logarithms. You would use a log actually to solve this equation. So right now we don't have enough math background in order to solve and continue with this equation here. You will next semester, but not quite yet. So what I want to do is try to estimate this as best as I can. Like for example, in estimating here, let's say I wanted to raise 2 to some power and have it equal 17. Okay, I can't obviously rewrite 17 using the same base as 2, but I do know that 2 to the 4th power, okay, is really close to 17 because it's equal to 16. I know that 2 to the 5th is 32, which is way bigger than 17, but basically 17 falls between 16 and 32, right? Which means that x must fall between 4 and 5. So when I would approximate here, I would say x is between the value 4 and 5. Now here it's the same idea. If I were to take 1/2 and raise it to the first power, I would get 1/2. If I were to take 1/2 and raise it to the second power, though, I get 1/4. Clearly, 1/4, 1/3, 1/2, right? 1/3 is between 1/4 and 1/2. So what we're looking at is an x value that's between this exponent and this exponent, 1 and 2. Okay, so we're just approximating for right now because we can't find the exact. So that would be our answer actually for the x-intercept. There is a value, it's just that it's between 1 and 2. So coming back to my key, you can see here that I write x-intercept here, and I show it over here. I don't have the specific coordinate, but I do see that it's consistent with the other 2 points. So that's going to be a clue for you too. If you see 2 points here and one is above and below the x-axis, then you can clearly see it should cross. So here I have just written between 1 and 2, comma 0. Algebraically, show your reasoning also. So I have, 1/2 to the first, 1/2 to the second. Therefore, that's what those little triangle dots mean. The x is between 1 and 2. Now, the summary of this, here we're seeing that as x increases, our y outputs decrease. So back to our table, if we look at our table here, as our x values increase, our y values get smaller, right? They get smaller and smaller until they finally get very close to -1. Okay, they don't touch -1, they don't actually equal -1, but it gets closer to that. What we call this is an exponential decay function. Okay, so an exponential decay function is the other type of exponential graph that we're going to look at as well. So that function looks slightly different. Here it decreases very rapidly and then bottoms out and gets really close to that asymptote, that horizontal asymptote. Okay? Okay, so to recap, the first 2 graphs that we looked at were exponential growth because as x increased, the y also increased. So that was a growth model. That's the general shape for growth. For a decay function, though, as x increases, so as we continue this direction in the x, our y value drops. It decreases and then it bottoms out and it has a horizontal asymptote also, but that's the general shape. Make sure you kind of get the idea too of the translations that occur so that you can get a better sense of how to graph something so that even when you don't know exactly what the function looks like, you can take a look at it and say, okay, this is clearly shifted down 4. It's also multiplied by 3, so this is technically a stretch, right? It acts like the a value in front of a quadratic or in front of a even an absolute value graph also. But basically, the better equipped you are to understand what's happening in the function, when you graph your table, it's going to make more sense too. All right, nice job. Sorry to ramble so much. I'll see you in class mañana.